visual SFM, a lot of people might not have found that, but there was actually also some higher level structure that was being searched in. Chang used this visual SFM tool as his general code base for all of his research he was doing, and in particular also here this work, for example, which was looking to detect automatically in images this type of large-scale, larger repetitions. So not so much what people had been doing at that time, very large facades with hundreds of repetitions, horizontal and vertical, of windows, but more a small number of mostly horizontal repetitions. The reason for looking at horizontal repetitions was the fact that the symmetry, there was not only repetition, but also symmetry. And this gave an interesting and easy to find kind of strong structure in the imagery, as we could actually, so if you look here on the right at the repetition, you see that not only is it repeating windows, but you can actually find like the repeating element, because there's both symmetry typically in the middle of the repeating element as well as between repeating elements. So you get two sets of mirror symmetries on between those horizontal repeating elements, which is not typically the case for vertical repetitions. So if we actually have this, we can even from a single image be able to recover even 3D structure from the slight shift in the symmetry, which you can, for example, observe here. The perspective means that what's in the front is slight structures that we could find, that these type of structures that we could find. Okay, I hope you can still hear me, as my connection seems to be somewhat unstable.
Yes, now, yeah, it's not bad.
Okay.
Now we can, yeah.
Yeah, I have a gigabit download and upload at ETH, but then every once in a while it seems to kind of disappear for a second or two. Sorry for that. So essentially what's really interesting is that these elements that we can find, so these elements that are repeating, turned out to be really strong elements for matching. With Chang, we did some experiments that show that we could essentially recognize a facade from widely different viewpoints at a very high rate with just a single feature, this single repeating window kind of pattern. We could beat out like typical facade matching structures with hundreds of features matched. We could beat that out with a single, by just finding the repeating element and then essentially characterizing it with a SIF type descriptor. So histogram, bins of histograms, essentially, that would be aligned to the repeating element. That this was a highly invariant descriptor that allowed us to do quite interesting matching. Okay, some other work we did in exploiting facade structures for geolocalization is this here, work that we did with Nokia at the time. So what we did was, on the one hand, at large scale, we could find, you know, from a database and street view type databases, plus building footprints from, let's say, OpenStreetMap type of footprints. From that, we could rectify facade images in our database on the one hand, and on the other hand, if we would get a query image, we could find vanishing points, do rectification of the different facade elements based on those vanishing point rectification, and then match those. And it turned out this was actually much more effective than matching directly the raw images, trying to match directly the raw images, which actually until now is still mostly the default to start from the raw images and extract invariant features there for geolocalization. So in this work, we showed we could get a big benefit from exploiting structure. And in particular, if you look at the bottom here, you can see that we could actually vote, once we had rectified the facade, we could actually vote independently for scale, for X translation and Y translation. And the interesting thing about this was that the X translation, for example, you see actually the structure of the facade starting to show up. We have a big peak, which was at the correct match between the two images here of the facade, but we get secondary peaks, which have to do with displacements of the repetition. So you see that these windows are roughly repeating, and so you see that structure show up here in the X translation vote, but not in the Y translation vote. Anyway, so very interesting structure in facades, and if you exploit it, you can actually get good results from this. This is actually showing this. This is a plot from our 2011 paper on the topic, which is a Chen San Francisco database for geolocalization testing. What's interesting here is the PCI is the normal unrectified, so the typical queries that people have been doing. So the essentially a SIFT baseline kind of on normal on the rocker images. And then we also have queries on the facade rectified images. And what you see is you immediately have a significant boost between the two. But actually more importantly, when you combine both, the facade rectified and the non-rectified ones, you get a very strong boost. So for a long time, people were in the, when they were comparing to the baseline, they just compared to the blue line, saying, well, they also only used these unrectified images, and therefore they focused on comparing to this, apples to apples. But if you would actually combine it with facade images and use the two together, you get actually much stronger response. This was with GPS, this was without GPS. So for a long time, people competed on beating the blue line, but were far from actually beating us on the combined approach. Now, why is the combined approach so powerful and beats out both approaches? Mostly because the facade rectified queries is super efficient, is super effective when you see a good facade and you can rectify it. Then it's way better than the other method. However, this doesn't always work. There are buildings that don't lend themselves to facade rectification. There are regions in the city where there is actually no facade per se to rectify. And so that means that when it works really well, but then sometimes it just loses out to a more classical method. The two together is therefore much more powerful. Okay, so if we look further at, in the meanwhile, how going from images to 3D structure has evolved, there are now tools like ColMap, done by Johannes Schönberger, who was one of my PhD students, and of Jan-Michael Fram's PhD students, and is now working at the Microsoft lab with us. So he's essentially now has developed one of the standard tools for going from image collections to 3D models, to large-scale 3D models. So you could think that with these type of tools, all the problems, all the problems of 3D reconstruction from images is kind of solved, and we don't really need additional structure to solve this type of problems. But I would like to show you a few places where there's actually a significant value, or there's still problems that are not tackled by these type of tools here. Okay. In particular, the fact that there is structure in 3D models, in actually existing architectural 3D models, man-made structures that are designed by architects, in general is great, but it actually causes surprising problems to our 3D modeling tools, which in general assume generics, have an assumption of genericity built in some cases. In particular, algorithms like ransack, robust matching algorithms, when they try to find, when they are trying to match images, they are looking for a non-random pattern of matches. Now, if an architect builds in this non-random, repeating structure, the algorithms can very quickly get confused. They find a lot of consistent matches in a 3D structure that is matching consistently, and they assume that therefore this must be a correct match. Okay, and what you see at the top here, A here, you see two completely unrelated parts of the facade at ETH that have, a high number of consistent matches between them. Because these are essentially structure matches and not actual matches of the actual location. At the bottom, you see even more worrying almost. This is actually the correct image, matching. However, it's off by one period of the window. You can actually notice this from the shade here, which is off by one in the matching here. It should actually, this window should match with this window and not with this one. Okay. Why does this happen? Well, it turned out the algorithm figures out that by matching this way, it can match, 4 windows to 4 windows, where if it matches the correct thing, it can only match 3 windows to 3 windows. And therefore, the structure overrides the actual correct matching because the structure is stronger than the actual correct localization. So what's the result of this? Well, it turns out that if you just run your class, your standard structure unaware structural motion pipeline, you can get in trouble. So in particular, typically still the standard approach for these photo collections is starting by building a relation graph. You try to match every image to every other image. Using some heuristics to be efficient. You find epipolar geometries between those, and that creates essentially a graph of all these pairwise, representing all these pairwise relationship between images. And then normally from that, you build up your structural motion, bundle adjustment, etc., and go from there. Now the problem is, if in this graph, you have some incorrect relations and you don't pay attention to it, you get a graph that looks like this here. And if you try to optimize it, you might get a completely scrambled reconstruction because it's essentially trying to, in addition to the correct structure, it might, for example, match one side of the facade to the other side of the facade. And so to this one, for example, here. So the left side to the right side of the facade. And then when it does that, it essentially will create impossible constraints to satisfy, and it will distort everything. Okay. So the approach to this that we proposed in this paper was to look and you integrate the transformations. The transformations should integrate to a okay, so my connection is unstable again. I hope you can still hear me. So if you do any loop, any geometric loop on this graph, you essentially should have the total accumulated transformation. So every edge here is a transformation, a relative geometric transformation. If you accumulate all of those, you should accumulate to 0 translation, 0 rotation, or a multiple of 360 rotations. So if you essentially sample many loops, you can find the ones that are inconsistent, that accumulate, for example, a 90-degree jump suddenly, which would mean that you match somewhere, one facade to the 90-degree off facade. And so by looking for which are the smallest number of incorrect edges I can cut to get a fully consistent graph, that's one way to resolve these problems. This is actually still an active research area. I don't think it's completely solved. It's actually a quite challenging problem. Okay. Now, a little bit later, after that work, we realized that the structure would not only hurt us, these kind of repeating structures would not only hurt us in 3D reconstruction, but could actually help us. It created these kind of structure relations between one side of the building and the other side of the building, realizing that these really look like exactly the same geometric structure is probably because the architect designed them to be exactly the same geometric structure. And so in that case, you can actually, in your bundle adjustment, add constraints, these type of virtual loop closures that allow you to have the left side of the building structurally be the same as the right side of the building. And you can include that in your bundle adjustment. And so by detecting those, you can actually strengthen the coupling in your bundle adjustment and get a much more consistent reconstruction, remove drift, etc. And actually also at the same time, finding these repetitions and symmetries will also give you the natural coordinate system for the building that's aligned to the main axis that the architect has used to design the building. So let me show you a video here illustrating this. So here's a data set of images. This was work from Andrea Cohen, my PhD student, but then also together with Sudipta Sinha, who actually had the original idea for this paper, seeing our 2010 paper. So what you see here is that this structure, that part of the facade here looks very similar to part of the facade there, that there's some symmetries and so on. You can get a much stronger resulting model here. Let me show you here the initial model of the building that I'm in. You see the distortion here. This should actually all be aligned. This should be nicely parallel. These are the symmetry planes we find. Both this part of the building is symmetric, these two sides are symmetric, etc. We can find a natural frame, and then we can include the constraints and essentially get a much more accurate reconstruction just by including these constraints in the Banana adjustment. Okay. I'm actually sitting somewhere in the back here currently. Okay. Here's some other ways to use symmetry. If you have a single image of a symmetric building, you can actually nicely use this as a stereo pair of the structure by mirroring left and right and seeing it as a stereo pair. Okay. This is some work we also did a while back. Then more in general, if you can detect symmetries also on the dense reconstruction side, you can actually leverage this to improve your reconstruction. So here for a stool with here five axis symmetry, here 5 different symmetry planes, discrete symmetry planes, we can actually detect those. As soon as you detect 2, by applying the symmetry to the symmetry, you actually get the full symmetric description of this tool, and you can have some completion happening between the observed legs, and the unobserved legs can all strengthen each other. And essentially what we end up doing is a regularization of our occupancy of our reconstruction, which is essentially predicting occupancy. We can regularize this now, including a preference for symmetric reconstructions. And here you'll see a few reconstructions. So this is a building that is partially symmetric. We will detect which regions are symmetric and which not, which regions are subject to which symmetries. So for example, here there's a symmetry plane, but it doesn't apply to the front part here. However, the second symmetry plane does apply to the front part. And this essentially just brings in specific regularizations. And then here you see now after completion or after implying this regularization, that's now non-local regularization between points that are subject to symmetry. So here you see some more results or more direct comparison. And you see essentially the effect of the completion here. So we have a reference model, then we worked with a lot less images, and so I have a less complete model, but then let the symmetry regularization do the work to recomplete the building, and actually in some cases even have a more complete building than what we had in a reference model because of occlusions and so on. We are missing some parts. Okay. Here's another place to use structure, to leverage structure. So in general, VIO is the standard way to, visual inertial odometry is a standard way to estimate your motion in an environment, as you see here, for example. This is actually also this building here, the building that I'm in today at ETH. What we did here was to leverage the fact that there's only typically a small discrete set of vanishing points in a building designed by an architect. And so we can use that to limit the drift. So of course, if we have a good VIO system, as you can see here, initially, you don't see much different. The drift accumulates slowly. In particular, the gyros are actually quite good at tracking, at not having too much drift. But over time, the drift will eventually accumulate. And that will lead, as you can see here at the bottom, to eventually significant errors accumulating. Because in our case, we essentially also estimate a discrete set, as you can see in the upper left here, a discrete set of vanishing points. So no, this is not a strict Manhattan world. It's actually more what some people call Atlanta world, where you have discrete vanishing points, but you can have more than 3. You see here, for example, this is actually, we just passed the office where I'm sitting now. My window is somewhere in the back here. You can see that there's actually 2 different main orientations for the building. But our system can nicely keep track of that and keep estimating, in addition to the normal filtering for the VIO, keep estimating also the best estimate for those vanishing points. And that way avoid accumulating drift, orientational drift over time. You still have a little bit of displacement drift, but it is much reduced. Other ways in indoor environments to leverage structure is here there was a lot of work you know, a number of years ago and still ongoing now with more modern techniques of essentially finding the structure of rooms. In this case, quite simple, just finding essentially a box to align to the room. And so some very nice work by Alexander Schwing and also in collaboration with Raquel to essentially find this optimally aligned based on evidence here that you estimate of the normals, the walls, and then you fit a box to these estimates. And this turns out to be actually quite easy and quite reliable in most indoor environments. And that gives you a ton of structure, which you then again can leverage for a number of different purposes. One thing we tried, for example, was then rectify each of those indoor walls and then do matching, for example, in that, and that was quite effective. If we go back to outdoors and look at facades, facades are strongly structured environments. And what we did here was work that actually leveraged really the fact that there's a strong horizontal structure of repeating elements, finding windows and balconies that have to be aligned here horizontally. And so in the end here, this whole structure can be determined by, you know, the choice of 3 lines: the beginning of the balcony, the bottom of the balcony, top of balcony, and top of window. Gives you 1 row of the facade, and exhaustive search with dynamic programming would give us a order and cube complexity. Some bounds, enabling us to estimate only a much smaller set of evaluations. So essentially, you see here the green dots are the points we actually had to evaluate because our bounds would not immediately exclude those to potentially give us an optimum. But so it's very sparse compared to the whole space, and typically this is a 2D space. Typically the space is 3D for these type of structures. And it ended up being only a very small fraction that we had to evaluate. And in addition, as long as we can estimate, as you see here, every row independently and they don't touch each other, also the bottom part and the top part here that are special cases don't actually overlap with the optimal facade elements we found. In most cases, we could actually prove that the solution we found was globally optimum. While still being only a few seconds for each facade labeling. Okay, so here the structure essentially allows us to also develop a very efficient algorithm to do this by exploiting that structure. So we've been indoors, we've been outdoors. What about connecting the indoors to the outdoors? That turns out to also be very difficult, and standard structure for motion has no solution for it. Not only are there very few contact points, I can of course look from inside to outside through the windows or walk through the door, but there's actually a significant problem there. Typically the exposure is very different. The brightness indoors and outdoors is very different. Most cameras don't capture a full high dynamic range, meaning that even if you can see elements from inside and outside at the same time, typically you can only see one of the two within the dynamic range. So either the inside is very dark when you see the outside, or when you see the inside features, the outside feature are all overexposed in most circumstances. So what we proposed to do was to leverage the semantic level, the structural level of the building, which is that the connecting element that you see from both sides are windows and doors, but windows is the most useful one, as there's many more of them. And so by finding the windows on the outside of the facade, by finding the windows in the indoor reconstruction, which from both sides independently is very easy, we could then align the indoor and the outdoor reconstruction very effectively by doing a robust window alignment scheme at the scale of the whole building. And so here you've seen now a few of those examples. Here's another line of work. So a little bit later, we revisited this in particular with some very interesting globally optimum consensus maximization methods. that would maximize the semantic overlap. In particular, we would use one reconstruction where we do a lower bound for the window. So if we detect a window, we'd find something inscribed inside the window, a shape inscribed to the inside the window. This would actually be quadrics that would be inside the window, and then on the in the other reconstruction, we do something that would be around the window, and then by combining both, by essentially having one align as well as possible inside the other, and this is something we could bound, we could actually align things. And here we've actually shown how you can do that both for hard day-night registration problems, for indoor-outdoor registration problems, or even for real scan to semantic CAD or BIM model and get very good reconstructions. So let me show you also here some examples in this video. So it's here day and night. You see one, we do the exaggerated shape, here the inside shape, and then we can essentially optimize having one always land within the other. Okay, so this is eventually what you get. Here's an indoor-outdoor reconstruction. And then let me get to the semantic one, which is quite nice here. So a 3D reconstruction of a building that's partially actually occluded even. So only some of the windows are visible. So here a bunch of scaffolding, but still we find enough windows to be able to automatically get the semantic alignment with the BIM model, as you'll see in a second. Go there, okay. So here's essentially, of course in the CAD, the windows are immediately labeled, so it's quite easy. And you see here a very nice, you know, accurate alignment between the semantic and the 3D reconstruction. Okay. Further in that direction, we also try to match the unmatchable, meaning essentially that, for example, a building like ETH, a very large building, there are a lot of trees around the building, meaning that it's actually hard to keep walking and have one sequence that captures nicely the whole building. You get trees and other things to occlude and break your trajectory somewhere along the way and make things unmatchable. So it's quite easy to reconstruct each piece of the facade. It's not quite possible to do it in a practical way, all in one kind of connected sequence. So what we did was essentially use then structure like building priors, symmetries, and semantic consistency to assemble in a plausible way the whole building. And we show that in most cases, we actually got quite nice reconstructions. So some of the things are aligning symmetries. If I have a symmetry in the front of the building and one in the back of the building, you know, they are most likely aligned throughout the building. Also, if we predict some plausible alignment, if we project one, you know, based on the predicted alignment, if we project one reconstruction in the images of the other reconstruction, we should have no semantic conflicts. What you see here in the bottom is a good alignment that's predicted, where we have the edge of the building actually project into, you know, on the edge of the other building. And so we get sky where we need to get sky, and we get facade where we need to get facade. Here, if we get an incorrect alignment predicted, we get conflicts with the facade here from one side with a wrong alignment projecting into free space in another view from another part of the building. Okay, so these were very explicit, very strong structural elements. There are also softer types of elements that are just related to a building consists of a number of different semantic elements. And if we leverage those, we can actually, in a softer way, we can actually get a lot of benefits also in our reconstructions. So here, I'm going to be very brief with this, but essentially, this is work that will essentially, from a collection of images, not only do classical multi-view 3D reconstruction, but at the same time also leverage semantic segmentation to get a better reconstruction and also a semantic reconstruction. So essentially we assemble, you know, evidence from both sides to then do one joint estimate of both the geometry and the semantics. Essentially what we do is a multi-class volumetric labeling. We solve a multi-class volumetric labeling or segmentation problem, where we segment the volume in voxels that contain building and vegetation and free space and ground, etc. What I want to convince you of is that not only by leveraging this structure, the fact that different elements of the scene behave differently, or we expect them to behave differently, we will actually not only get a more useful reconstruction, because we now know which part is a building, for example, but we actually also get a better reconstruction without changing anything on what we get in on the geometric side. Okay, so here's one example. This is a square in Catania. This is the reconstruction you get here on the left, purely from geometry. And then you get essentially the same exact, on the right, the same exact geometric information used. But in this case, we actually have different parts of the scene behave differently based on what they represent. So if I represent ground, this is a top view. If I'm a voxel or a surface element that represents the ground, then I like to be, to extend horizontally. When I'm a building, I like to have vertical facades. And so simply the regularization is different, but the data term on the geometry side is identical. Okay? And you see that qualitatively, you get a completely different reconstruction. Where here we regularize just for minimizing surface area, explaining as much as possible the data term, the geometric data term, but minimize surface area as a regularization. A semantic class. Okay? What you see qualitatively is that we get the whole surface, the whole ground from the initial data terms that's only at a few sparse places. The whole ground, okay, so connection is bad again. So the whole ground diffuses out to fill in eventually the whole square. And once the whole square is filled in, the part of the building that's missing here on the left side can nicely be filled in, because once the ground diffuses under the building, then the building can nicely continue and complete itself until it stands on the ground, which is the natural, building expectation for the regularization, that it's somehow going vertical until it hits the ground, and there it just connects straight to the ground. Okay, here you see a direct comparison between what you get from just geometry, and then once you add this structure, this semantic structure to your reconstruction algorithm, and have different types, different semantic classes behave differently in a pure regularization sense. Still very simple regularization, but anisotropic and class specific. Okay. Now you get so not only do you get a better reconstruction, but also here you get better in the sense that if you just do regularization that's class agnostic, you actually have no reason to separate the building from the vegetation. And if it turns out it's cheaper to connect the tree in the unobserved part to connect it to the building, because that's less surface area, that's what you would do. However, if we reconstruct separate classes, then we really have no reason to do that, and we'll have the building be completed as, closing the simplest way to complete the building, which is, having a flat wall, flat vertical wall, and then separately the vegetation will be closed from behind, and they will not touch each other actually. They could, but if there's no reason for them to. Also, the layers, you can easily separate them and now, count, for example, the volume of the building, get a terrain elevation model, like with the buildings and vegetation taken out, etc. And, like for CO2 kind of carbon, you could kind of estimate how much carbon is available there in the vegetation. Okay, how is this done? Well, I won't go into any details here, but the first method we proposed here, or the typical methods, are actually using both this, a data term, geometric data terms here, which essentially, as in many methods, they say, well, I expect if I have a surface measurement at a certain point, I expect just in front of it to have empty space, behind it to have occupied space. And so I would expect to see a surface somewhere over here. That's our geometric data term. And so we take all the images from the depth maps and map that into the volume. So all the data gets translated from image evidence, which is directional from a certain point. I want free space and then a surface. I actually have to ignore some of that and just translate it to a data term in the volume. And then at the same place in the volume, we then have a regularization term applied in the volume, which in our case is class specific, but an anisotropic, but it's still somewhere, it's in the volume. It expresses what we expect, you know, these structures from these structures in kind of generic, in a regularization term. What is a prior, what is likely? Okay, and we combine both in the volume and then optimize in the volume as a multi-label problem. We optimize this. So that's this method. But there's a big shortcoming. By translating everything to the volume, we actually have to simplify things and ignore a number of things. In particular, that if I reconstruct the surface somewhere, I should have free space in front of it. You could impose directly a free space constraint, but that would cause other problems and would actually still not resolve really the problem we have. So the correct way to actually formalize it, and so for comparison again, everything translated on the axis, which is on the volume, on the voxels itself. In this case here, in our new formulation that uses higher order array potentials, we actually have, similarly to here, a term in the volume, which expresses the regularization and what we expect to see for the 3D scene. So this is a prior on the 3D scene, which is class specific, etc. But then we actually have something that goes back to the evidence in the image and correctly expresses the evidence in the image. So essentially what we have is really array potential, which connects now all of the voxels along the ray. So this is very expensive, but it correctly expresses visibility. Visibility is actually one of the hardest things to treat properly. And often if you treat it properly, you have to start ignoring all other types of constraints. And so it's essentially visibility is very hard to correctly incorporate in any optimization in computer vision. So in our case, what we did was we have all the voxels along array. And what we want to express is that we have free space up till here. And then the first voxel we observe, if it's occupied, that actually tells us directly what our depth is. And the specific label this has is the label we should see in the image. So we should have compatibility between what we observe and what's actually in the volume. Okay. So the way we express that is as follows: with one, everything is was still convex except one constraint per pixel, which is a non-convex constraint, but it is differentiable actually, as Tutsani noted. There's one constraint that expresses that, you know, we have the global view in the volume. This is where regularization happens. And then we have a per camera auxiliary volume, which is defined, has empty space defined up to the first pixel, non-empty pixel. And then after, behind that, we have nothing defined, okay? But the first empty pixel, the first non-empty pixel here, and which is the only non-empty pixel along array, that pixel here cannot have, that's what this constraint expresses, cannot be more, you know, filled with, you know, needs to have exactly the same class, or in other words, is bounded by what you find in the same voxel in the other place. So if everything is, if we have empty and then first voxel, we need everything empty here along the same ray and the first voxel occupied with at least as much of that particular label as we see here. And then this constraint, of course, is directly on this volume. We can trivially express our data term and optimize our data term. So in the end, we have this, we regularize in the volume, and the data term is actually minimized between, in some sense, re-rendering our volume into the viewpoint of the image. And what's minimized is the difference between our observations and the re-rendered model. And so this is actually a fully correct formulation of this problem. Sadly enough, it is actually a very expensive formulation, but it actually is very effective, but quite expensive. Okay. What was surprising?
If you can finish maybe in about 3 to 4 minutes, it would be great to have some time for questions and answers.
I'll do that. What was interesting was actually to notice that, and actually I still checked today, it's still state of the art, at least if you select this here. In just the two view case, even without using semantics, It still defines the state of the art on the Middlebury here. It also allows very nicely to treat thin surfaces, for example, which you would see from both sides. Okay. So this rate potential method is actually very powerful. Okay. Now, as today, when you have to solve complicated problems with a number of priors and so on, typically we would go to machine learning methods now. And so also here we actually show that, you know, these very slow methods here, going back to the initial method, the other one being even slower. The initial method needs many, many iterations to get to a good result. Here we can actually learn a multi-scale network that will, in a fraction of the iteration, in a fraction of the compute, get to qualitatively an equivalent reconstruction here, semantic reconstruction, but with everything essentially learned from data, and also learn to be kind of very efficient in solving the problem, as opposed to the kind of very solid mathematics, but that then needs to take small steps to guarantee convergence of the classical methods. Here's some more work, which I'll skip for lack of time, but some recent work on scene representations using deep learning methods. And this, if you're interested, you can see during the week later. Also, of course, important is finding instances. So not only the general structure of the space, but then inside the space, finding specific objects. Let me very quickly go through that. This was some work we did that could find essentially these instances as separate chairs, for example, etc. Was doing quite well, but of course this was ECCV. But of course, you know, a few months later, there's this very active, and so a lot of people have worked there. So to finish, just wanted to quickly show some work on finding, you know, very specific indoor structures and where essentially we find like this Manhattan world assumption. We, you know, do a number of filtering steps and processing steps, find a number of planes. Because of the Manhattan world, we can do simple one-point ransacks, be very efficient, find the ceiling, the floor, then find the walls, segment the space in different segments, and then start combining those segments in rooms. And then you can both generate floor plans and CAD models. Okay, so here's some examples. Pretty good results. This was at IROS a few years ago. Let me skip for this and just show you that in HoloLens, which is of course a fantastic device to do a lot of real-time computer vision with, tons of sensors, both depth sensors and camera sensors, a chip here to do all the processing, the real-time computer vision-based processing, and leave essentially your Qualcomm processor in the back free to do your own applications and run things on. The reason I want to quickly show that in this context is beyond the VIO system, the depth camera that essentially, you know, builds up continuously these kind of 3D models of the environment. If you accumulate that over time, you can actually get very large scale models of the whole space you traverse with your device, just walking around it essentially, not explicitly scanning, just using the device in that environment. HoloLens 2 has the capability with this DNN core to do real-time semantic segmentation of what it's seeing in front of its sensors. And so here, color essentially the scene like this. And so to finish this here, essentially, this is essentially a large scale. This was half of Studio A floor where people walked around with HoloLens, built this whole 3D map. And then you can actually here as an illustration, you can run by accumulating this semantic segmentation info and then run this type of raw 3D model to more CAD model or floor plan. You can extract all of this nicely and automatically from this data. And to conclude, so structure can sometimes hurt. Repeated structure, spatial aliasing, or what we often call wormholes, connecting one part of space to another because the algorithms, the robust matching algorithms, get confused by seeing the same structure. You know, think of also different floors of a building that has, you know, all the floors look alike, etc. You can very easily collapse your 10th floor high building to a single floor building by having all those floors somehow connected to each other. Having many more symmetries across floors than stairs that give you evidence that they're not connected, that they are different floors. And so overrule the graph. But of course, in many cases, structure can really help. Symmetries, Manhattan world, architectural rules, also more generically, the shape and function are connected, meaning that if you can semantically recognize something, it tells you something about the shape and vice versa. And so this can really be used to regularize a lot of reconstructions. And I'll leave it at that. So thank you.
Thank you very much, Marc, for very impressive sequence body of work from days before learning to after deep learning. For those of you who join later, you can type your questions into chat or Q&A, or you can raise your hand, click raise your hand if you want to ask question live. If you speak, it would be great to mention your name and affiliation, if any, before speaking out. Maybe I can start with a question. So both you and I know the days before deep learning, 3D vision was very exciting, revolutions. So somehow to me, deep learning didn't add much to 3D vision for maybe the production side, the impact, whatever that means. So to me, somehow what we achieved in 3D vision revolution before deep learning, how much we could add by having deep learning, maybe 9 before deep learning, only 10% deep learning added. I wonder, how do you measure? Is it similar from your impression? Because you know HoloLens. Do you see deep learning actually maybe added more than 10%? How do you weight revolution before deep learning, after deep learning in terms of 3D vision applications?
Mm-hmm. I think it depends. So I think we're still figuring out. So the initial, so deep learning obviously revolutionized things like recognition and so on, which is, essentially there was very little structure, or people had been able to find very little structure in the problems, very little underlying mathematics that could really kind of, strongly describe the problem. Contrary to what we had in 3D vision, with very, very strong mathematics, very strong insights in how exactly this all relates, and with essentially, in a sense, highly nonlinear, things, kind of equations and so on, that we can evaluate very efficiently, and we figured out how to use those, but they're actually kind of highly complicated and nonlinear, and we have simple equations that allow us to essentially work over the whole range of space, like the 6-dot space, for example, 6-degree freedom space, or other things. So we have these kind of closed form equations that very well cover the whole space. And, the simple approach that on image labeling problems and so on were very effective of just end-to-end learning everything from a ton of data, turned out to not really be applicable in 3D vision, because it's kind of silly to throw away all these, these very compact small equations to somehow then explicitly have to learn the whole space. Especially in deep learning, you have to learn the product of structure and motion. So it's, like once you start doing that. So we have very compact expressions that somehow disentangle structure and motion. If you want to do that with deep learning without anything else, you would naively have to do structure and motion, that product of all possibilities of the motion and the structure, exhaustively sample it in a sense, to be able to learn and then, learn that those functions that we have derived. Okay, so clearly doing that is kind of, essentially stupid and doesn't work. And so, but that doesn't mean that you have to, say like, okay, deep learning is not going to ever apply to 3D vision. No, there's many other parts of our pipelines that actually are much more heuristics based. Somehow we've tuned things to kind of do well, to kind of somehow cope with a number of things. And all of those parts of the pipelines, they are very amenable to be learned from data. And so what what you see now, but this is only, the first wave was naively applying things, didn't work, failed to kind of actually deliver. Now you see people going in and go pick, figure out which parts of the pipelines make sense to replace. For example, what we showed, like the TSDF part, they're going in and actually learning that, there's a few things that are kind of ignored in TSDF. Like if you see like, oh, it's this kind of thing. Oh yes, here we should do this and that, because it's like I'm at the edge of an object or I'm this or that. This is something you can very easily learn from data, and then have something that somehow does more the right thing than the naive kind of simple method that that TSDF would do, for example, in reconstruction. So I think there's lots of potential. We're still partially really figuring it out. I think it's really important to leverage as much as possible the explicit structure, the explicit mathematic descriptions that we have. Concepts like the invariance, like the different things that we really understand and can explain compactly mathematically, we should keep using that. That gives us a ton of invariance, means that we have to learn a much smaller space, right? And therefore, just can deliver much better solution. But so like it's finding that trade-off. But so yes, I think more than 10% can be obtained in terms of engineering, of really making solid systems that can cope with a lot of circumstance, but it's only going to work if we find the right combination between the two, and that's still ongoing.
Thank you, Marc. So I have one. Want to pick. We are running out of time, but I want to pick one audience question. So I'll just read it. I like the semantics reconstruction of the whole floor based on the HoloLens device. Mm-hmm. How important is it to have a 3D floor plan as prior knowledge, or is it just a floor plan with a bird's eye view sufficient?
So here the floor plan was obtained fully automatically from the HoloLens data, from just walking around the floor. But I would say that if you have a floor plan in advance, it's fantastic. Like it can avoid any drift. It can also be used, for example, to, if you already have existing digital information defined with respect, where things are with respect to your floor plan. If you have the floor plan and then you just walk around the space with the HoloLens, you can actually very quickly, easily match the two. And if you do that, you can copy over all this digital information to the real world in front of your eyes, to pop up in front of your eyes with the HoloLens. So if you have a floor plan and if there's information in that floor plan, that's super useful. Yes.
It seems like it should be 3D. It should be a 3D floor plan.
2D, 3D, doesn't matter.
2D is okay. I see. That's great. Yes, thank you very much. So we already a bit past a few minutes. So I'd like to thank Marc again. Can you, if you stop the screen sharing, I can move on to Niloy. And thank you very much again, Marc.
Thank you.
Yes, so Niloy, you can start screen sharing while I will do the introduction for you. Yes. So our second keynote speaker is Niloy Mitra. So Niloy is a professor at the University College London. He got his PhD from Stanford University under the supervision of Leo Guibas and Marc Leboy, really one of the most influential researchers in geometry processing and computer graphics. Niloy won the ACM SIGGRAPH Significant New Research Award in 2013. If you don't know, this is an award which basically says Niloy is the best researcher in graphics in the coming generation. It's a very prestigious award. Niloy also won the BCS Roger Needham Award in 2015, Eurographics Outstanding Technical Contribution Award in 2019. And he also won the ELC Starting Grant in 2013. He's really the expert in geometry processing CAD model from the graphics side. And we're really excited to have Niloy to give the second keynote. So Niloy, please start your the talk. Oh, sorry, you're still muted. Maybe I can unmute you. Yes. Let's see.
Can you hear me?
Yes.
Yeah. Thank you, Yasu, for the introduction, and thanks to Yasu and Yi for the invitation. It's really a privilege to be here. As ideally, we should have been in person, but this is remotely. So it's a nice follow-up of what Marc talked about. Marc showed like years of amazing results on reconstruction from real data using structure and symmetry, topics that are very close to my heart. So in this talk, I'm going to talk about the other side of the problem, which is generation. And when I talk about generation, as I would explain, is generating what I call parametric representations. And I would try to argue why this is important. I'm going to talk about 3 of our very recent work on this topic, because they're very much related, and you would see how they are linked as we go ahead. So let me start by showing a problem that we have in computer graphics and generally in creative content creation domain. That assets for games and high quality production are still largely created manually. And this is extremely expensive. So if you look at the at the building on the left, this can easily take like half a day of very skilled artists to model, and can be like $4,000, $5,000 just to create a single building, and only the outside of the building, not even the interior, as Marc was showing. And the reason it's expensive, these are model polygon level, almost floor level and element level, and then they are textured. This is super expensive. And this is typically a screenshot of the system where it's modeled, where each element is modeled, and on the top you can see a huge number of annotations and step level operations that one has to do. It doesn't quite scale. As a result, if you look at creation of even one street of high quality data, this is a slide I borrowed from Andrew Price. It's just for a single scene, it can take like $2,000 to create this. And that's why games and movies have millions of dollars in budget for creating digital content. Okay. Now, with learning-based methods, where we have models in the form of maybe Street View data, Google 3D View, etc., we have shown that it is possible to have generative models that creates buildings. In this case, this is a reconstruction of the area around my University College office in London, where you can see our method can produce mass models, semantic elements like floors and windows and doors, and then also add textures to this. Right? Now, while the quality is very promising, there are certain things that we don't like about this, which is it produces still polygons, it produces still texture maps, it produces still only the exterior of the building, and miss the structure that Marc was talking about. So the question we started asking, can we do more, knowing how the world is structured around us? In this work, I will talk about three aspects. The first one is about appearance. How do we create textures? And not texture as images, but texture as a procedure or as a program. And then I would shift to a complementary aspect of geometry, which is shapes, and then also how we think of not only creating geometry, but programs that when executed creates geometry. And I will talk about an object level, but it's also we would like to extend to scene levels. So let me talk about this first one about texture space. And this is inspired by very classical problem that we have, that suppose we get texture. So you take your phone, you move it around, you take your favorite textures all rectified from your worlds. These are small texture patches. Then the question is, can we create, so this is taken from a phone, can we create a space where each of these images get embedded such that we can now walk in this abstract texture space, and each of these along as we move along, we can do interpolation of these textures that you see here. But this is not only restricted to 3D, we can also leave them to, sorry, not restricted to 2D, we can also go to 3D. Now, there are certain requirements. We want this to be diverse in the sense, as we go outside, every time we generate this grass texture, it has to be stochastic, and it's not like the same texture being shown every time, so that there's no scene boundary. It has to be continuous, as you can see, so we can query at runtime. So it's not limited by a small patch, but as big as the canvas we want to be. We also want like infinite zoom, so you can zoom in and out of this texture. So the question we ask is, how can we create this? Now in computer graphics, starting from Perlin noise that Perlin introduced in '83, there's a very classical way of generating textures. This is showing in 3D, but the method is understood in 2D. So it has three main steps. So it has a step where random directions are assigned to grid cells. The second one is how these gradients are interpolated at a query location. And the third one is some sort of a smoothing. As a result, we get infinite texture, but it has a very classic Perlin noise style, but it's guaranteed that it would not repeat because it's stochastic in nature. The question is asked is, knowing the structure, can we come up with a network or a network structure? And that's what I would explain, that can take a set of images as exemplars and then create create textures at runtime. And this is not limited to a particular location. As I mentioned, we can query at any location X with the particular style, and we would get this infinite texture. Okay? So the whole point is, how can we make this happen? And I'll try to explain this. So what we do is, the first step is we need to capture the style of this texture patch, which is quite easy to do. We train an encoder that maps it to some latent vector Z. So this is quite standard, but the fun starts sort of now. So what we want to do is, we want to take this style. So this style is capturing if it's a wood texture or stone texture or a type of wood, etc. And then we have this MLP structure, this H function, that learns to produce matrices, which is TIs, and element E. Now, as you will see, these TIs are actually transformation matrices, very small in this case, in the 2D case, 2 by 2 matrices, as we will see. And these deterministic transformations that the network would output is then going to be used as an input for generating a noise. And I will explain all these blocks as we go. This zeta 1 are the seeds to the noise function, and the position is an encoding of where on this image we are. Right? So this is a location, because we want a noise in location 1 to be different from the noise in location 2. Right? So that's the setup, and I will explain the blocks individually now. Okay, so the first, let's look at the H function. So what we do with the H is, we want to take the latent vector Z, and then we want to generate these transformation matrices. So just bear with me, I'll explain why and how these transformation matrices are going to be used, but let's first create these transformation matrices. Now these are translation, rotation, and shearing, so we can express them as 2 by 2 matrices. So we have a block that, almost a decoder block that takes a Z and writes out these elements, which are explicitly converted to transformations. So it's a simple way. We are taking the 2 by 2 elements or matrices and flattening them out and representing the vector. But these are, we do not have direct supervision information about these AIs. These are directly constructed as we go. Okay. Now we can take any location X and apply transformation to this and seed it with this zeta i's. Okay. Now, what we're doing here is, we take this noise function, and this noise function essentially gives a shared rotation, as you see here. So there's a stack of noise that is generated. And the shape of each of the subimage is determined by the transformation or the shearing by the transformation T1 or T2 or T3. So what it does, it takes a standard grid and distorts it according to the learned transformations Ti that is position dependent. I'll show it again. Okay. So that's the structure of the network. And then what is happening essentially is, the position information is coming out from the X vector, and depending on the learned transformation Ti, this grid is distorted in different ways. Okay. And then conditioned on this distorted grid, we have a noise function that generates noise in the different cells. And this turns out to be exactly what we needed to recreate Perlin noise, but in a learned MLP setting. It's going to be much more powerful than standard Perlin noise. So that's the location-specific encoding we have. And then we can learn the second nonlinear block with another MLP that takes the noise along with the element and produces a texture. Now, what is the supervision data? So we're not going to compare this patch with the original patch because it's noise. So the pixel level comparisons just does not make any sense. So what we want to do is, we want to do comparison, but in a more abstracted sense. So what we do is, we compare what's called the gram matrix, which is a correlation of the VTG features at the patch level. This can be trained end to end. So this highlighted block can be seen as the structuring. This is the structuring information we know and we expect from the requirements, that it's infinite, and it's diverse, that it's not repeating, it has zoom level, etc. All of these information, a requirement is used to structure the structuring block, to organize the structuring block. So that's our contribution from our graphics background of how to structure the network. If you take this whole block as one block, then it's becomes the decoder of the encoded of the signal that we encoded using G. Right? Now, the reason this works is the information or our knowledge we have about Perlin noise and other types of noise functions in graphics to structure the block. It's not like a standard decoder we could have used here. And that's the main thing we want to emphasize, which links back to what Marc was saying, that if we know if we have a lot of knowledge in a particular domain, we should use it in structuring the network and hence expect it to work. So let's see how we would train it. We could train it in 2D, or we can also train it in 3D. So then the exact same correlation has to apply, but not in the volumetric one, but in random slices of this. Okay, so now we have done the hard part. We can look at some results. So we can interpolate between two exemplars. I'll show it again. So if you see from the left to the right, and as we interpolate, we get grass of different types with or without flowers. It's also very computationally efficient, and we can only probe it at the points we need. So we don't need to generate the texture. We can just generate the texture code, and we can probe as we would need. So if we go back to our facade examples that I showed as a motivation, now we don't have to store this very high resolution texture image, but only the neural texture code that we can probe at runtime. And it will be diverse by construction, or we can also lift it to 3D. In this case, in the marble example, this makes more sense, but it's still possible to show it on the grass example in 3D. Okay, so moving from appearance, we now move to geometry, the topic which is very close to my heart, where we are going to talk about structure in the sense of the structure of objects and the structure of parts. And I will talk what I mean by structure. And this is a series of work we presented at SIGGRAPH Asia last year, and also CVPR this year. And I will only be able to talk about part of the work here. Okay. So the problem we are investigating, and it comes up across many domains, is often we have very structured data. As we have seen, we have floor plans that comes with size of the rooms, aspect ratio of the rooms, but also how they are connected. And it's not just at the level of buildings, even at the level of cities. So this is a map of road networks in UK. You can see that the connection of the points are very important. So the underlying connectivity structure is we also want to reconstruct. In graphics, there's several examples. We can have layouts as structure. We can have patterns. We can have symmetry, repetition, regularity. We have scenes represented as scene graphs, and we'll see that in the last part of the talk. We have compositions in the image, and also if you follow the way in which artists generate high quality textures, they are generated in form of what's called substance graph, which is really a graph of a procedure which executed generates very complex textures, as we see here. So the question we are asking is, what is the right representation to learn on, and how do we learn with these structures? And that's what we are going to show, and hopefully this is a method that's going to be very useful if you want to work with structured data. Now, I want to motivate this by showing that if we lack structure, we have models directly as point clouds, for example, we can still do point clouds-based encoding and do interpolation in the latent code, but then we get these sort of chairs in the middle, but somehow they don't look like chairs. They look like chairs from a distance, but the more you look at it, they look like a blur because they are a blur. So it's unclear if the middle model has chair arms or not, or if they have the slats underneath or not. But if we explicitly encode structure in the learning process, as we will see, we would get this type of intermediate interpolations. So this is a preview of results. First I will explain the method, but this is a preview of the result. You'll see it not only generates point clouds, but says this is a leg, this is an arm brace, this is like a slat between the two legs. So it's very, very explicit, and we don't have this fuzzy result anymore. So what are the challenges? There are several challenges if we go from image domain to voxel domain to point cloud domain to structure domain. One is we have to jointly handle geometry and topology, or how the parts are connected. So this is in the level of chairs, it was parts and how they're connected. In the level of floor plan, it's rooms and how the doors and windows link across them. Also from interior and exterior, there's windows that's connecting the spaces, as Marc was showing. So we have to handle both continuous and discrete changes, and we don't quite have the same number of parts. So a room might have, a floor plan might have 10 rooms, another might have 5 rooms. So how do we handle this varying number of parts? And since there are no fixed number of parts, the correspondence is also unknown. So what we are trying to do is we have this collection of chairs. I will use the chairs as a running example. And then we are trying to create a latent space. So that's the goal we have, such that any model or any point from it can be decoded to a chair. And any observation, whether it's an image or a point cloud or even just a depth scan, can be encoded back to the space. Okay. So the whole next part of the talk is how do we design our structures, this encoder and decoder. Now, for this, the representation we were going to choose is a graph, where we have the graph for the connectivity and the nodes for the geometry of the parts. So we are assuming we have a part-based model. So that's an assumption we have now, where the vertices are just bounding boxes of the individual parts. And the structure of how they're connected are based on a graph. And this graph will encode if parts are connected as in adjacency, or parts are related non-locally using symmetry. And I will show examples later on. So why do we have a graph? So we have a graph, but it's also a hierarchical graph, and I want to emphasize this. So if you look at these two chairs, so on left and right are the corresponding graphs of the two chairs. So you see the base and legs and here, and as you can see, the graphs are different. But because we have a hierarchy of parts, so as we move up the hierarchy, then even very diverse looking objects where the geometry is very different can have very similar graphs. And this is quite good, because now there is hope that we can find a consistent graph that can encode it. So let's look at the problem we have at hand, which is we have an arbitrary graph, which is hierarchical, and this is a collection of them, and we want to encode them into a single vector in the end. So the approach we take is the following. We propose a recursive approach that goes from bottom up, and this was motivated by the original GRASS algorithm that was developed from SFU in Richard Zhang's group, but now we have a completely random graph without requiring binary connections. So what we are going to do is we are going to take subgraphs and merge them into meta nodes. So here the yellow and blue one has been merged into this purple one, and we continue this process. So it's a recursive one. So this is the encoding phase. We keep merging until we get to a node. Okay. I haven't talked about how we can take a subgraph and merge to a node. That's a problem we have to explain. Now, in the decoding part, we will go the other way. So we'll start from a node, we will start decoding into subgraphs, and we will stop when we will, under certain condition. And now we have an encoder and decoder that takes a shape, maps to a latent code, and gets back up again. Now, there are certain problems with making this happen. One is, when we are decoding, we don't know when to stop, so we have to solve that. When we are decoding, we don't know if my siblings, if I will have like 2 siblings or 5 siblings. So the number of subparts are not known at that point. And also, if you look at the encoded and decoded, they may not have the same order, because there is no canonical order here. So if you could look at the leaf level, the yellow and the blue nodes are sort of switched. So we have to account for that when we compare reconstructions. So because this is inherent, we cannot assume consistency where we don't have it. It's a bit like matching the unmatchable, as Marc was showing in one of his examples. So to list the problems we have to solve, we have to encode and decode subgraphs that I have to explain. We have to invariant under the sibling ordering. We have variable number of children, and when to stop the recursion. Now I'm going to talk about the main parts here. So the way we are going to diffuse information in the graph is using graph convolution network. For those who haven't used it before, it's quite easy to understand if you have a background in general neural networks. So what is happening is we have features available as vertices or nodes, and edges are the connectivity information. For this version of graph network, it's only edge connections. We are not working with probabilities yet on the edges. Or the edges don't have features. It's whether they exist or not. And the output is each node, we want to have a feature of depth f. Right? So that's what we are trying to do. So it's an iterative approach. It's like a message passing, where in level L+1, we diffuse information given the known graph structure according to adjacency information to update the features at each node. And this amounts to a fixed nonlinearity given by the sigma, and learning the weights, this W matrix, on this graph. So if you are familiar with geometry processing, this is essentially a Laplacian representation of the world, and we are trying to update the weights according to diffusion based on Laplacian matrix. And this can be written explicitly in this form, where this Wij is diffused according to the neighborhood information given by the CIJs. Okay, so this allows us to take a subgraph, and I will talk about these tau values in a minute, and diffuse the information according to the known graph structure along the orange edges here. So it's diffusing this information. And at this stage, all the nodes get the updated features. And then we have to account for that we do not have a fixed ordering among the nodes. So when we collect the information from them, we have to take an operation which is invariant to the node ordering. We take the max in this case. You can also take min or sum would also work here. So that allows us to take the subgraph and map it to a single feature, in this case, FIT. So that's a feature for the whole subgraph. I did not talk about how to handle multiple number of children. You have to refer to the paper, how you would do this, and also a condition of when to stop the recursion. Okay, so now let's look at some examples. So again, these are three different models with their corresponding graphs. And the way we are encoding the structure or the symmetry relations here is we have translational symmetry. So in this case, and we also have reflectional symmetry here about the vertical plane. We also handle rotational symmetry. Marc showed an example with a chair with like 5 order of rotational symmetry for the legs. And we have another relation, which is not a symmetry relation, but the adjacency relation if two parts are connected or not. That's given by the tau wave. So that's how we get the graph. And this is our model. So a chair in this hierarchy, and then a hierarchy of parts. And when we reach the leaf level, that's each part of it, whether it's a leg or a back or a seat, etc. Now, how do we encode this? We have talked about the encoding that we go bottom up. So we start from them and recursively try to merge them, subgraphs into nodes. And then we have a shape in the latent code, and the decoding is the opposite of that, and we get this. So what are the losses? There are 3 types of losses. 2 of them you can imagine. The third one is going to be interesting. So the first one is the reconstruction loss. We take the point cloud of the left, point cloud of the right, we compare. So that's a standard law. The second loss is an interesting loss, and this is again where knowing the structure and knowing how the world is organized helps. So that's what we call the structure consistency loss. It's essentially comparing at a graph level. And this is the interesting part. This is what gives it the power. And when we compare the two graphs, we cannot assume that we have correspondence. So we have to solve for the correspondence at the graph level inside the training part, and we do it with the Hungarian matching. One observation here is because we know that the graphs are hierarchical and we have the hierarchy, we can exploit that in the graph matching. So it becomes a much simpler matching problem than matching all the sets of nodes to all the sets of nodes. And the final one, because we have a BAE formulation, we have a variational loss in the latent space. So that's these are the specific components of the reconstruction loss, point cloud to point cloud. And then I already explained about the structure consistency loss, where we are comparing the graph, both if the node exists or not, or if an edge exists or not, and also if the edge type is correct. So we have two types. We have an edge and also a type of edge. We compare both. Okay. So now we can start from a graph and progressively encode it from the bottom of the chair to the top. And in the end, we get a feature vector for each of the leaf nodes. So that's the geometric encoding. And then each of the subgraphs, we have a feature, that's a feature graph. So we go bottom up and we, in the end, get a single latent code for the entire object or the structured object. Decoder, we have already seen this. We start from the top and go down. First, we have the graph-based decoder. And once we reach the end or the leaf, we get a geometric reconstruction. So this allows us to do several applications, and that's one of the power of being able to create such a latent code. It's difficult to create, but once we can create, we can unify many applications. So this is trained on the partner dataset that was released at CVPR last year. So the first is the reconstruction, and reconstruction means given a shape, can we get back its graph? So it starts from an input point cloud, and we can reconstruct it here. Now note that one of the output is we reconstruct the graph. So we can start with a point cloud and directly come up with the structure for that, which is what we call the projection step. And this works better than any of the previous methods, particularly we compare to graphs, which assumes that the underlying graph is binary, and removing that had a significant improvement on the performance. You can see the reconstruction error improves or reduces drastically. We can do shape generation. This was our main goal. So we can decode, we can sample from the space and decode, but we decode not only the point cloud, but the point cloud along with the graph and structure. These are several generation results, both at the box level or at the point cloud level. Note that the point clouds are colored because we get their association along with the semantic labels, which is what's important. It allows us to do interesting interpolations, and I already showed you a preview of this result. So now we can interpolate between diverse shapes, but at the same time preserving the structure in between them. So now we don't have a fuzzy blob in the middle, but we know if the chair arm exists or not, or the slat of the between the leg exists or not. So there's a very specific decoding that's happening here. It's not only restricted to chairs, it also extends to other data sets where we have these part levels annotations available in the training data. So this is on the cabinet data set. And you can see that the number of shelves or the number of drawers are different for different cabinets, and it finds a really semantically plausible interpolation. So in this case, the left is interpolating from the left column to the right column, either at the box level or at the point cloud level. It allows us to also do a projection step, which is one can think of a shape abstraction case. So this can be either a point cloud, a depth scan, or even an image. And here we are showing images captured by a Kinect. It'll be very cool to see how well it will work on HoloLens reconstruction, as Marc was demonstrating. And what we can go is from an input image to go back to the reconstructed shape, which does the completion of the object along with structuring the object. So the way we pose this is, now that we have a latent code, we restrict the reconstruction into the latent code. And that's the regularizer the latent code is providing. So we can go from the original point cloud to solve a reconstruction problem, but restricted to the learned latent code, which is often much more compact and much more structured than the original point set. It allows us to get this grouping, whether in the full point cloud or in partial. It also gives us a powerful tool to now think of analogies. So we can take a shape and another shape, so A to B, and we can think how it would translate to this new shape. And the way we do this in the CVPR paper that I would not present here, but I'm just giving you the main idea, is how can we transfer a vector in the latent space to another vector. And what we show in this paper is not just doing a direct latent code arithmetic, but creating a latent code that directly encodes the edits. So we are not encoding the shapes, but we're encoding the shape differences. And that allows us to create a very nice and intuitive analogy. So in this case, to appreciate the difficulty of the problem, it's a edit being applied to a chair with arms, while in the input, this part was not even included. So we made the chair wider, but in the edit, it made the chair wider, but also applied it to the arm, because in this model, the arms are present. Okay, so as you can see here, that's what's happening in this example. Okay, so I will instead spend the remaining time I have, the next 10 minutes or so, on going to the next version of this problem, which I think is, we're very pleased to get this result. So which is just has been accepted to SIGGRAPH Asia this year, where the problem we are formulating or we're investigating is, can we take these structures and directly generate the programs? The programs which when executed will create these shapes. So if you go back to the original motivation I showed when I showed the AutoCAD screenshot, so it says it's writing out the program which when executed will create these shapes. Why do we want to have programs? Because somehow programs are very hard to write. So if you see on the right, these are programs which when executed gives the chair. This is somehow the gold standard. These are really good. This is how we would like everything to be. But there are certain advantages. Now, when we change these programs, we change the parameters of this, we will get more valid chair outputs. That's how artists would draw them. The difficulty is we need an expert to even author these programs, and that's what we are trying to replace. So once we have them, they are great, but it's hard to get them. Also, we cannot directly obtain programs. We have very limited amount of data, so we can't generate them very easily. So we need to do a lot of tricks to be able to generate programs. On the left is the most traditional, in the deep learning context, the latent space analogy, where we take this and directly output a point cloud or a structured point cloud, as we have seen before. The advantage is this can be trained directly with data, so we don't need an artist to create this latent space, so it's great. But then control, providing a control on that is rather limited and is application specific. So we are trying to create a hybrid space that takes the learning from the left world and outputs the program so that we have the controls that we're familiar with. Now, each of these, so to reiterate, the goal we have is we are creating this latent space, which we will sample, and the sample will give this block of code, which when executed will give the shape, right? So the output is not the chair, the output is the program. And that's what we are changing. I do want to emphasize one thing here, that the programs are going to be hierarchical or functional. In the sense, first we will be defining chair as a composition of chair arm, chair back, etc. Then when we execute the back command, it would give the geometry of the chair back, etc. Okay. And then we can interpolate in this space. So think about this. It allows us to interpolate between two programs, which is unclear how to do this, but in the latent code world, we can do this. And when executed, it would again get a valid chain. Right? So that's the problem we are trying to solve here. And we can edit them to get newer variations. We have talked about this, and we sort of, this hybrid space allows us to interpolate in the latent world and then do the parameter variations in the program world. Okay. So I need to define a domain-specific language. This is a contribution of our paper, where we decide or regularize the problem by saying these are the instruction or these are the operations we will allow. And let me walk through them because it's not quite intuitive what we're doing here. So the first level, the top left, we just start with defining a collection of bounding boxes of different dimension, and the color denotes which box it is. Right? So, and they are all in a common canonical coordinate. Okay? So these are creating the parts. The next part are these operators, which I will give some examples of this attach and squeeze, that relatively places these modules. Right. Again, we saw part of this in Marc's talk when you were showing these rooms and then adding the symmetry constraints to get everything correlated and regularized. That's what these attach operations are doing. And once this is done, this is progressively done because it's hierarchical, and it also has the symmetry relations. So let me show you some examples of this attach operation. So if between the blue and the green box, if they are attached in the red point, that means these red points have to be co-located or snapped. So this is with a single attach point. There can also be two attach points, and that allows us to get these non-axis aligned locations. Note that all the red points are in terms of relative size of the whole object. So it's not absolute values, it's fractional values with respect to the bounding box. So. And then finally, we have the squeeze operations, which is a fancy name for saying if you have two parts, the orange and the blue, the orange and the green, and the blue part we are saying is squeezed between them. So the dimension has to be extended or compressed so that it becomes flush with the two primitives. Okay. Now, this way of attaching the operations with attach and squeeze, and also with symmetry that we can consider, allows us to reduce the number of absolute coordinates we have to provide, which are now restricted only to the bounding box phase. So here's an example of the full execution of one chair block. We are still talking about the language that's allowed. We define a chair as a composition of base, back, etc. And the base is then again another function call that gives the cuboids, which are the dimension, and then they're defined how they are placed or positioned. So you can think of this the squeeze, reflect, and attach operations are sort of the edges of the part level graphs that are being done. Okay, so that's the language that we have, and the question is, how can we directly output these languages? We're not going to execute the programs at training time, but we are directly trying to get this. So this amounts to a sequence generation problem. And the way we are going to do this, we are going to build a VAE directly on the program space. So it's a sequence translation problem, and you can imagine which tricks we are going to use there. And the programs are going to be extracted from our ShapeNet dataset that was trained on PartNet. Okay. Now, because we want to output a sequence, the natural choice would be RNN, but we went for GRU units for doing it. And we are again going to use the hierarchy structure that we already have. So we're going to leverage that. So at each of these hierarchy levels, what we have is we have some child node coming in, very similar to the structure node block that we had shown before. But now, instead of decoding that into the geometric nodes along with their symmetry, their edge types, what we are going to do is we are going to output the lines or instruction lines that that will give us the the geometry along with the relations when executed. So these are the line 1 to n, so it will go sequentially and it will go 1, 2, 3, 4, etc. In the paper, we discuss a lot of details about how to make these programs canonical, because that's one of the requirements for this to work. And we propose ways of making the programs canonical and not depend on the ordering and how to break the ties that happens because of this ambiguity. And that's quite essential. If we don't do that step, then the whole training would just collapse. And that's why it's important to understand the invariance, in this case, the symmetry types and the ambiguity in the numbering of this, and have specific steps in the algorithm that that also remains invariant and under line ordering in this case. The decoder would be, once we would have the variational setting, we have the mu and sigma. From that, we will decode a node. This node can be either another subprogram or a leaf geometry, right? And depending on that, we would recursively do this. So you can see that going by the z child. So if it should be recursed, it will go down. Otherwise, it will stop there. And to expand out the line decoder, these are going to be a sequence of these things. There's too much details to go into here, so I will leave that for the. So let's look at the results. It allows us now to create samples, which are in the middle row, and on top and bottom, we fetch the nearest neighbors from the data set to show that the network, in this case, the shape program, is actually learning something interesting. So the top one are the nearest neighbor probes based on geometry, and the bottom one are nearest neighbor according to program distance. And you see that it's different from both. So it's really learning to interpolate in a different fashion than retrieving nearest neighbor. Here's our examples, and you can see that compared to StructureNet, which works at the geometry level, our outputs are more stable because they have the programmatic structure. And we also do some physical stability tests that I leave for the paper, but under that, we come out to be much more favorable because they are much more stable with more feasible center of mass, etc. And so for a different data set, in the cabinet data set, and the column on the left, the 3D PRN ones, so those are another method that directly learns on programs, and you can see one of the earlier methods that started this type of directions. You can see ours is significantly more structured than that because we're exploiting the hierarchy. Yeah. I'll try to wrap up within the next 3 to 5 minutes. That would still keep us on track. Okay. It allows us a new handle. This is a handle we were not familiar with before, of allowing interpolation, but through the space of programs. As you see on the lower one, on the top one is the interpolation on StructureNet, which is still reasonable, but it's still not quite programmatically valid, particularly the middle one. It seems like 3 floating parts without the top bar, but at the program level, we don't have these problems. These are interpolation on the cabinet class. And again, you can see different number of shelves appearing on the left, on the lower part. And what we're showing here are the executions of the program. That's not the output. The output are actually programs that says number of parts is 5, number of parts is 2 or 3, etc. We can now go and directly edit the programs. So these are editing the lines of the programs. We can change the parameter both as the extent of the bounding boxes, or we can say that change the number of slats from 5 to 3, etc. Here's an interesting graph. I find this particularly informative about what is really going on. So let's look at the graph on the left. So what it's showing is how much of the total shapes we can represent after by how much fraction of the programs we can represent. So the more the graph is on the top left, that means it's very compact, that even with 2% of the shapes, we can, these are already represented in once we have a few programs. Right? So the more the graph goes to the top left, it's more and more compact, and that's more and more desirable. The baseline being we need equal number of shapes for programs, which is the diagonal line here. So you can see that we have a steep gain at the beginning across all classes, but the storage class turns out to be more difficult because it is less, there is less sort of canonical programs for cabinets. The space of variations of cabinets is more. If you go to the right plot, it's very similar, but now we're doing at the level of parts. And then we see all the programs are much better because now we have factored out the geometric variation in some sense. We're only looking at the topology of the parts. And then all of the methods benefit very quickly by working in the space of programs. It allows us to, of course, synthesize from input point cloud. We can go directly to programs now. So it's again a projection step, but in this case. So to try to wrap up the part we have seen so far, so we have talked about the texture, the structure net, and then also the structure, the shape assembly program. So there are certain common limitations. So in the last one, we have a handcrafted DSL, handcrafted domain-specific language. In the texture case, we have a handcrafted structure of how the noise model should be, motivated by the Perlin noise. And it would be nice to also be able to directly learn this. The output we have produced are often abstracted representation, either in the level of programs or in the level of boxes. And the next thing is, can we go and add details to this? Not the point cloud sampling, but actually geometric details in the point of meshes. That's something we're working on. The third part that I think we are not yet doing in this work is we haven't coupled the geometry and the rendering stages yet. So these features are explicit features, not any deep features that we're learning. And the final point I want to say is the type of controls are still a little bit behind than what traditional computer graphics allow us. So in graphics, I can go ahead and add details to any particular part of the geometry. I can go ahead and change the texture of a particular wall, or I can go ahead and add 20 more boxes or 20 more cows or animals in a particular landscape, and they will all be consistent. We are missing this object level control at this stage. So I want to show one example of results we can have now, and I would not talk about this paper, but it's on our webpage, which investigates the last question, is how do we add control to geometric synthesis? So here we are going to a different world. We are going to a world where we do not directly output appearance or geometry, but we directly output the image. So we are directly outputting the projected image rather than individually the geometry and the texture. And this decoupling, or giving away this decoupling, allows us to now create very, very high quality edits that I think were not possible before. So these is starting from images. We can do edits like here, and I hope you would also be surprised by the quality of the edits. But this is showing one interaction where we are moving the light from left to right. Here we are showing an example where we are moving the face from left to right or changing the camera. And just look at the quality of the fidelity of the images and try to think of your best sort of algorithms you have out there and how you can do this quality of edits, where the edits are the traditional graphics one, but the quality or the fidelity is what we would expect from a camera. And that's what we're trying to do. We have been successful in the face domain, but there's so much to be done across other domains where the topology and structure is different. So to summarize, I mainly talked about 3 projects. The first one is, how can we create materials in this neural texture synthesis world? How can we link topology and geometry for generation? And then generating shape programs. And this is, I hope this is only a way to get you guys excited to work on this problem, because we need a lot of help in this domain. There's a lot of problem that remains to be rethought, because it has the potential of changing graphics pipeline, as we know, that has been used for decades. Because now we can do things that we could not do before, which is really encouraging. And then if we could learn from really in the wild data as the ones that Marc showed, the potentials are just impossible to predict now, but I think it's very exciting research-wise. And also in terms of practical application, this can open up very new tools for creative artists that is of very much interest to me. So with that, I will like to stop and take questions. Please visit our website. We have code and data available for most of the project. For the last one, since the work has just been accepted, the code is not yet available, but should be there within a few weeks, latest a month. Okay, thank you.
Thank you very much, Niloy, for a very impressive talk. We have some audience questions. We are a bit late in the schedule. I want to use them to ask. I hope that ECCV will not cut this Zoom session at the 10 a.m. sharp. The first question is from Jiang Fei Kai, I believe, from Nanyang Technological University in Singapore. So his question slash comment was, nice talk. Do you assume the hierarchical graph is available in advance? If so, how to deal with the cases if we don't know the graph? This is for the second project.
Yeah, I will. Thank you. So I will try to give short answers just because she said there's a few of them. So this is a really excellent question. In this case, we assume the hierarchical graph is given in the form of the PartNet dataset. However, there is a paper last year at SIGGRAPH Asia where, from Microsoft Asia, where they presented a way to come up with this hierarchy directly from data. So to go from a set of meshes to directly come up with parts and their hierarchy. So that would be a very natural thing that we want to try. Can we use those learned hierarchy for this one?
Thank you. So his next question is from Isaac Ben Shabat. Sorry if I pronounced it wrong. I believe from Australian National University in Australia. This is for the second project. Does this assume that the object class is known? To add my question, is the model trained per category or across all the categories together?
Yeah, very relevant question. It does not assume the models to be trained per category, but I would argue that if the categories are very diverse, for example, chairs and cabinets, this probably doesn't make sense to be for them to be trained together because these would be just different modes in the latent space. But it is meaningful to do, say, chairs and tables together or chairs and benches together. And in our paper, we show examples what happens when the categories are semantically and not semantically and graphically similar, and hence the latent space is meaningful. If we train 20 different categories, it's of course much harder. They end up with their 20 individual clusters. It's not quite meaningful to use that because the intermediate interpolations would not be relevant.
Thank you. So let's take the last question again from same Isaac from Australian National University. This is for the third project. How do you differentiate through the programs? I believe this is about the backpropagation. How do you backpropagate to the program?
So this is a sequence generation. So I want to say a couple of things. Because we are using GRUs and not a transformer network yet, future nodes cannot influence the previous node. So that's one problem. The way we differentiate through them is differentiated through the lines of the programs. The lines of the programs are represented in a very, very long one-hot vector, where each line can be a cuboid, an attach, a symmetry operation, etc., squeeze operation, etc. And you can differentiate through them. And the cost is going to be, am I getting the operation, the line right or not? Now, this has a problem. This has the advantage that we can differentiate. However, certain types of error are more costly than others. So, for example, if we have a big bounding box versus a smaller bounding box, maybe this is not so bad in terms of the reconstruction, but in terms of the program, this would get a high penalty. So it's a more conservative approach of differentiating through them. But because they have been applied in the sequence learning case, So one can differentiate through this one-hot encoding of this. If you have any further questions about this, please reach out to me via my email, and I would be happy to explain that and also provide pointers.
Great. Yeah, thank you very much again, Niloy. I'd like to thank Marc, Niloy, and also all the participants for joining the workshop today. As I mentioned at the beginning, we also have pre-recorded talks with the other exciting speakers on the website. Also have the panel discussion session later today at 4 p.m. UK time in 6 hours from now. So hope you can come back again to watch the exciting discussion later today. Thank you very much again, and that's all for the first live session. Take care.